Hello students, welcome to this next video. In the last video we have seen that what is a second shifting theorem. Second shifting theorem says that if you have L of f of x is f of p, then L of f of x minus a u of x minus a is e raised to minus ap f of p, or you can say L of f of x u of x minus a is e raised to minus ap L of f of x plus a. So these were the equivalent statements 1 and 2. These were the equivalent statements of second shifting theorem, right? Okay, so now we will see, and we have seen that how we can use this to find the Laplace transform. Now we will see how we can use this to find the Laplace inverse transform. Now if you write the equivalent forms for Laplace inverse, you will get that f of x minus a into u of x minus a is Laplace inverse of e raised to minus ap fp, right? Or if you write the equivalent statement here, you'll get f of x u of x minus a is L inverse of e raised to minus ap fp. Laplace of f of x plus a. Let us not give it a name, right? Now let us see how we can use it in the questions. So you have this question: find L inverse of e raised to power minus 3p upon p plus 2. So if you recall all the properties which we have done for finding Laplace inverse, there is no property which will help you when there is a multiplication with e raised to power minus 3p. So you have to use second shifting theorem only. So now you see, if you compare it with this, that L inverse of this, right? So this is, you compare it with this is e raised to minus 3p into 1 upon p plus 2. So this will be your f of p, and you want L inverse, so that will be f of x minus a u of x minus a here is 3, a here is 3, and f of x is, right, that is L inverse of f of p. So that will be L inverse of 1 upon p plus 2, so that is e raised to minus 2x. Fine. So you will get here, this is f of x, and this is equal to f of x minus 3 u of x minus 3. So this is equal to, this function is 0 for x less than 3. So this is 0 for x less than 3, and this function is 1 for x greater than equal to 3. So x minus 3 for x greater than equal to 3, and your f of x is e raised to minus 2x. So your answer here is, this is an answer to this, is 0, and here you will get e raised to minus 2. In place of x you will write x minus 3, x greater than equal to 3. For x less than 3 it is 0. So this is your answer to Laplace inverse of e raised to minus 3p upon p plus 2. So you see how can you use the second shifting theorem for finding Laplace inverse. Let us do one more thing. Find L inverse of e raised to minus 2p upon p square, right? So your a here is 2, right? And if you compare it with, this is e raised to minus 2p into fp, so this is your fp, right? So by second shifting theorem, this is equal to f of x minus 2 u of x minus 2, where f of x is L inverse of 1 by p square, so that is actually x. So this is equal to 0 for x less than 2, and this is f of x minus 2 for x greater than equal to 2. Now your f of x is x, so f of x minus 2 will be x minus 2. So the x minus 2 for x greater than equal to 2, x less than 2, this is 0. So this is equal to Laplace inverse of e raised to minus 2p upon p square. So this is how you can use this second shifting theorem to find the Laplace inverse. Now I want to tell you some results which can be used in some problems. We are done with the syllabus, so let us do, if you want to find out what is Laplace inverse of unit step function, Laplace transform, sorry, not inverse, transform of unit step function u of x minus a, say. So you want this u of x minus a. So how you will find it? This is equal to L of 1 u of x minus a. So you treat it as f of x. By second shifting theorem, this is equal to e raised to a minus ap L of f of x plus a, right? By second shifting theorem. right? Now f of x is 1, so f of x plus a is also 1, so this is e raised to power ap l of 1, which is 1 by p. So you have to remember that Laplace transform of u of x minus a is e raised to power minus ap upon p. This will be used in some questions, so you can remember it. Now next result is, there is something called Dirac delta function, right? So I'll first tell you what this function is. This function denoted by delta of x is a function which is 0 for x not equal to 0, right? It is everywhere 0, and at x it is infinity, right? In such a manner that if you integrate from minus infinity to infinity delta x, you will get a unit number, right? In actuality, if the functions which are known to you, you will not be able to find any function which satisfies this thing which I have written here, right? So you may think that this is not possible to define a function like this, but it turns out that in higher mathematics there are something called distributions, and then we have functionals. In those like areas, such functions exist, right? And why this is important? Because this function is used to model many situations, like a unit, if you have a unit mass, right? Or you have this unit charge, so point mass, point charge. For modeling point charge means a point charge is at only at one point mass, right? This function is useful. Okay, anyways, let us not talk about that this function, whether it exists or not. It exists for sure. So, and if we are talking about here delta x, if I'm talking about delta x minus a, this is a function which is 0 everywhere except at a, and at a it is infinity, in such a way that minus infinity to infinity delta of x minus a dx is 0, right? Okay, fine. Is 1, not 0, is 1. Fine. Now I want to know what is Laplace transform of delta of x. It turns out that this is e raised to power minus, if I have Laplace transform of delta of x minus a, it turns out that is e raised to power minus pa. Fine. So I'm not going to prove this like rigorously, but I can give you an idea that how you can prove. Suppose if you take Laplace transform of x delta x minus a, so you see what this will be. By definition, this is 0 to infinity e raised to minus p t delta px delta of x minus a dx. Now you see this function is 0 everywhere except at a point. Okay, let us make this this is 0 everywhere except at a point a. 0 everywhere except at a, right? So it means that when you will take the integral, so you will get a 0 everywhere except at a, and at a, x is equal to a, the value of this function is e raised to minus pa, right? This will be out of the integral, and then you have 0 to infinity delta of x minus a dx, right? And because a we are assuming is on the right hand side of your axis, 0 to infinity, right? And there is nothing on the left hand side because this is 0 everywhere anyway, so this is equal to e raised to minus pa minus infinity to infinity delta x minus a dx. So this is 1, right? So your answer is e raised to minus pa. So I am saying that this is not a rigorous proof, just an intuition that how you can prove that Laplace transform of delta function is e raised to minus pa. So we will see such these two formulas which I have just written may be useful in solving some of the problems. Let me do the problems. So you have this question, solve dy by dx plus 4 0 to x yt dt is equal to f of x, where f of x is defined as 0 for x less than 1 and it is x for x greater than 1, and y of 0 is given to be 2, right? So let us see how we can solve it. First of all, you write this in terms of unit step function because we know we will use the Laplace transform. So I am writing dy by dx is plus 4 0 to x yt dt. On the right hand side, I know I can write this function as 0 plus x minus 0 into unit step at 1, right? Now take Laplace transform on both sides. So you will get here s, or whatever, if you want to write p, it's up to you, L of y minus y of 0 plus 4 L of y. This is, see, now you, if you take Laplace transform, I'm sorry, this is not L of y, so here you have Laplace transform of this thing. So you know that Laplace transform of integral is Laplace transform of the function divided by s, right? We are using that formula here. Now this is Laplace transform of x u of x minus 1, right? Now here you use the second shifting theorem. So this is here x, you don't have x minus 1, so this is e raised to minus a is 1 here, p s into Laplace transform of f of x plus a, fine, because you have x only here. So this is e raised to minus s L of x plus 1. So this is equal to e raised to minus s, Laplace transform of x is 1 by s square plus 1 by s. This is equal to 2. So you will get s plus 4 by s into L of y minus 2 is equal to this thing, right? So from here you can just write Ly, you can bring this 2 on the other side and then you can divide. You'll get Ly equal to 2s upon s square plus 4 plus e raised to minus s plus 1 upon s into s square plus 4. So this is what you will get. Now we want to take Laplace inverse. Take Laplace inverse. You see, so many calculations are involved. So when you take Laplace inverse, on the left hand side you will get y. So here you will get 2 L inverse of s upon s square plus 4, and here you get L inverse of s e raised to minus s plus 1 upon s into s square plus 4, right? So this first part is easy. This is 2 cos of 2x plus L inverse of e raised to minus s plus 1 s into s square plus 4. Now you see here you will use this second shifting. Second shifting theorem says that, you see, this is your e raised to minus s into a function. So this is the Laplace inverse will be f of x minus a, right, into u of x minus a, where a is your 1, right? You are using second shifting theorem here. A is your 1 and f of x will be computed as L inverse of whatever is this, s plus 1 upon s into s square plus 4, right? So we have to find now this. Later on we will come to this point, right? So we'll just save it. First we are finding this quantity now. Okay, so let us do this. So you have s plus 1 upon s into s square plus 4. You can write it as, I want L inverse, so you can write it as L inverse 1 upon s square plus 4 plus, you can just separate it, right? First you take this and then this. So you have 1 upon s into s square plus 4, right? So this is equal to, here you will get 1 by 2 sine 2t, and here when you divide with s, then you have to integrate from 0 to x of whatever is the Laplace inverse of this, that is sine 2t dt, right? So here I am using that L inverse of f of s by s is 0 to x ft dt, this property we had, right? So this is 1 by 2 sine of 2t plus 1 by 2 minus cos of 2t by 2, 0 to x. So you get here 1 by 2 sine 2t minus 1 by 4. Here I'll write in x, okay, x, and then you have minus 1 by 4 cos of 2x minus 1, right? So you get 1 by 2 sine 2x minus 1 by 4 cos 2x plus 1, right? Now you go back here, we want f of x minus a, right? So you had this, that y is equal to, you have y is equal to 2 cos 2x plus f of x minus 1 u of x minus 1, where fx is this, right? So you can just write it like this, or you can just simplify it. So this is 2 cos of 2x plus f of x minus 1 for x greater than equal to 1, because then it will take this value, and otherwise it is taking 0 value. So you have 2 cos of 2x for x less than 1. Now you can just put f of x minus 1. So this is 2 cos of 2x plus f of x minus 1. Replace x with x minus 1. So 1 by 2 sine of 2x minus 1 minus 1 by 4 cos of 2x minus 1 plus 1 for x greater than equal to 1, and it is 2 cos of 2x for x less than 1. So this is how you will solve the problem. Let us do one more problem, and that is the last problem. Solve y double prime plus 4y is equal to fx plus delta x minus 1, where fx is 1 for 0 less than x less than 1, and it is 0 for x greater than 1, and you are given that y of 0 and y dash 0 are 0, right? Okay, so you solve it. You can just first you write this in terms of unit step function. You see, I can write it as 1 plus this function. I can write as 1 plus, you have 0 minus 1 into u x minus 1, right? You have to be careful, 0 minus 1. So I have y double prime plus 4y is equal to 1 minus u x minus 1 plus delta x minus 1. Now I want to take Laplace transform. We'll get s square L of y minus s y of 0 minus y dash 0 plus 4 L of y is equal to, on the right hand side, for 1 you will get 1 by s. For this function I just told you that the Laplace transform is e raised to power minus s, because a here is s, 1 upon s, plus for this function we just saw that the Laplace transform is minus as. A is 1 here, right? Okay, fine. This is 0 given, this is 0, so you have s square plus 4 L of y is equal to 1 upon s minus e raised to minus s upon s plus e raised to minus s. So you get L of y is equal to 1 upon s into s square plus 4 minus e raised to minus s upon s into s square plus 4 plus e raised to minus s upon s square plus 4, right? So this is what you get. Now you just have to find. So this is going to be this. Now we want Laplace inverse, right? So for that you have y is equal to L inverse of first quantity s square plus 4, then you have minus L inverse of e raised to minus s into s square plus 4 plus L inverse of e raised to minus s square plus 4, right? Here you see we just saw that this will be 1 by 4, because for this you have sine 2t upon t upon 2, then you divide with s, so you have to integrate, so you'll get 1 by 4. We just got in the last question 1 by 2x, right? And here you see you have e raised to minus s into 1 upon this, right? So that is second shifting theorem. This is equal to f of x minus 1 into u of x minus 1, where f of x is this function, because the Laplace inverse of this function is same, right? Is equal to 1 by 4, 1 minus cos of 2x, and here 1 upon sine s square plus 4, that is Laplace inverse for this particular thing is 1 by 2 sine 2t 2x, and when you multiply with e raised to minus x, so you will get it as 1 by 2 sine 2x, right, minus 1 into e raised to power into u x minus 1, right? So this is your solution.